In section 2.7, we're going to talk about implicit differentiation. Now, first, let's define what we mean by implicit functions. And before we actually talk about implicit function, let's talk about explicit functions. Okay, so up to now, we defined y as a function of x in this form, as a y equal f of x. Now, for example, let's say I have something like this, y equal 1 over x, something very easy. Now, what makes this explicit is that y is isolated by itself and it is written explicitly as a function of x. Okay, now if we multiply both sides by x here, we get xy equal 1. Now this is the form of a function that is implicit. So implicit versus explicit. Explicit means you have y isolated and x would be on the other side of equal sign. That would be y as a function of x, like every function that you've seen so far in this course and before in your other classes. Once you combine x and y together, then it's no longer explicit. In fact, the general form, the implicit form of any function is like this. The implicit form of a function, we're talking about function of two variables, one dependent, one independent variables, is in the form of f of xy equals 0. So for example, xy equal 1 can be written as xy, let me fix that one. Okay. It can be written as xy minus 1 equals 0. So you see how that is in the form of a joint function of x and y equals 0. Now, the reason this is important for our work is because in this section, actually, we're going to be able to take a look at differentiation through functions that are implicitly defined. And this will enable us to find the derivative of these more complicated functions where I cannot always solve for y. Okay, in other words, we cannot differentiate directly, or it's very difficult to differentiate it directly. So as a consequence, we're going to differentiate these implicitly. Okay, so let me show you an example of how this works. Okay, so let's actually proceed with finding the derivative of 1 over x. And let's say we want to evaluate this at some point at, let's say when x is 2, y is a half. There we go. We want to find the derivative at that point. Okay, at that we want to find y prime. So using the power rule, I can do this. Notice right now it is in explicit form, right? So I can use the power rule. That's negative 1x to negative 2, or negative 1 over x squared. Now y prime evaluated at when x is 2 is going to be negative 1 over 2 squared, or negative 1 quarter. So nothing new. We've done this before. And this is how the explicit form works. Now, let's do this implicitly. Now, our biggest assumption, by the way, here, when we do implicit differentiation, is that y could be written as a function of x. So let's do that. Our assumption throughout this whole section is that y is a function of x. That's all we assume. Okay. So let's revisit that problem. So we had xy equal 1. Okay, we want to find the derivative implicitly. Now, if y is a function of x, then I can write this as x times f of x equals 1, correct? Now, let's take the derivative of both sides. Now, the right side, the derivative is 0. Now, on the left side, we have product, right? X times f of x. So we're going to actually apply the product rule to this one. So that would be the derivative of first by second plus first times derivative of second, right? Product rule. And at this point, let's actually solve for f prime x. F prime x, let me put one step in there. So we get x f prime x equals negative f of x. And to solve for f prime x, I'm going to divide both sides by x, so I get negative f of x divided by x. Now at this point, usually we leave it like this, and we can find the derivative at some given point. But remember, I can replace f of x with y, and I get x is negative y over x. And this is the implicit form. Notice in implicit form, I still have y in the final answer, so I don't have it entirely in terms of x. So there's a y in there. But remember, if I solve for y here, we can do that for this particular one. In other instances, I cannot do this. That is, I cannot solve for y, but the assumption still holds that y could be theoretically done as a function of x. And if I plug in now, if I plug in 1 over x for y, then I get negative 1 over x squared. So notice it's exactly the same thing as we had earlier. And let's say, so that's what the derivative is. But keep in mind, oftentimes we don't do that. When we do implicit differentiation, we will have y in the answer. Okay, so now let's do f prime of x evaluated at the point that we started with at 2 and 1/2. Evaluated at 2 and 1/2. So I'm going to use the implicit form, right? Negative y over x evaluated at 2 and 1/2. So that means I'm going to plug in 1/2 for y, 2 for x, and half divided by 2 is negative 1/4. Look, we got exactly the same answer that we got earlier. Okay, that's what we had. So it's just another way of doing this, a clever way of doing it. The key is to recognize y is a function of x. So for example here, where we took the derivative, we applied chain rule, so we have f prime x. Okay, now let's take a look at some of these examples. Okay, so let's take a look at number 4. We're going to start with number 4. In exercise number 4, the question is x squared y plus 2x y squared negative x plus 3 equals 0. Okay, and we want to find dy dx by implicit differentiation. Okay, now notice, by the way, in this one, it will be difficult to solve for y, wouldn't it? It would be. And I could solve for y, of course, but it's going to be complicated. Okay, so for example, I can write this as 2x, just to show you real quick how I could do it as solving it for y, plus x squared y, okay, x squared y, plus 3 minus x. What I'm doing is I'm writing it in ay squared plus by plus c, so I can use quadratic formula with this, right? So it's a quadratic formula. I'm going to see this as a quadratic formula in y. Okay, so the solution to y is plus or it's a negative b, so that's negative x squared plus or minus square root of b squared is x to the 4th minus 4 times a times c divided by 2 times a. Notice how complicated this is, and this isn't the derivative, this is just y, right? It's the function y. And just one more step here, x to the 4th, I'm going to distribute and combine like terms, so it becomes x to the 4th, 2x squared and x, that's 4 by 2, 8 positive, 8x squared, and 3 times 8, 24, negative 24x. And again, this is just y explicitly written in terms of x. Now we have to find the derivative of this if we wanted to do it this way, but keep in mind we don't want to do it this way, and that's why it is so important to be able to do this implicitly. It's a lifesaver the way we do this. using implicit. So this, I'm just going to say dot, 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 and it continues on for many steps later. And there's so much room for error in this one, and we do have to take into consideration the plus minus in front of the radical. So now let's do this using implicit differentiation. Now remember, the assumption is y is equal to f of x. So just as we did earlier, let me scroll back up. Just as we did with this example, anytime we take the derivative of f of x, that's going to end up with f prime of x, right? Now, I'm going to actually keep this in with y instead of f of x, okay? But keep in mind, anytime I take derivative of f of x or y, there will be an f prime x or y prime. So the first term, we're just looking at this one, x squared times y. That's the product rule onto itself, right? So, excuse me, if I take the derivative of x squared, that's going to be 2x, right? That's 2x times y. Derivative of first by second plus first times derivative of second. Well, derivative of y is y prime. And then we have plus 2x y squared. So that's constant multiple. Derivative of first, again, because it's a product rule in here. Now, derivative of x is 1 times y squared plus x times derivative of y squared is 2y, power rule, and then y prime. Remember, anytime any derivative, when we do implicit, any derivative that involves y will be accompanied by a y prime, because of that part of it is like chain rule. Next, derivative of negative x is 1, derivative of 3 is 0, derivative of 0 on the other side is 0, and there you go. Now let's tidy up this thing. I'm going to group my y primes together, okay, and I'm going to write it as x squared, and then we have 2xy plus 2xy, and then y prime, right? That takes care of the two terms having y prime in them. And then I'm going to combine the next two terms, this one and this one, together. That's plus 2y squared plus 2xy minus 1 equals 0. There's also a negative 1 there, right? And let's see, I've got 1, 2, 3, 4, 5 terms. 1, 2, 3, 4, 5 terms. Yeah, looks good. Okay, now next step, we're going to isolate y prime. So, y prime equals, going to divide by the coefficient on y prime, and move everything, these three terms, move them to the other side. So it's going to be 1 minus 2y squared negative 2xy. They change sign as they move to the other side. And there you have it. We managed to do this, and that is the answer to this exercise. Okay, notice it's like, whoa, how come I don't have just x in there? You see the y here, the y here? That's the nature of implicit differentiation. So what good is this for? Well, if I'm given a point, I can find the slope of a tangent at a point because I know both x and y. And that's usually what we want to know. We want to know the rate of the change of a function at a given point. So this comes in very handy. But if I want to actually go and solve for y prime just entirely in terms of x, I have to do this, right? So that's not going to be trivial. Okay, so we're done with this one example. Let's take a look at another one. Actually, you know what? I just saw something right in here. 2 times 2. Okay, actually, it looks okay now. What I did is I forgot to distribute 2 times 2 here initially, so I did that. That changed something here, and then in the denominator I have to change that to a 4, right? And also, if you want, we can actually factor. Let's do that. Let's factor the denominator, so it's going to be x times x plus 4y, 1 minus 2y squared negative 2xy. Even that we can write it in descending powers of y. How about this? We can write it like that if you wanted to. There. So this would be like a polynomial in y squared. Or in just y, not in y squared, in variable y. And there you go. So we're done with this example. Now let's take a look at another one. Let's take a look at exercise number 10. In exercise number 10, I have x plus y over x minus y. X plus y over x minus y equals y squared plus 1. Okay, now for this one, we're going to again do implicit differentiation. So that means on the left side, I'm going to do quotient rule. Remember, any derivative that involves y has to end up with a y prime. So I'm going to square the denominator, x minus y squared. Repeat the denominator times the derivative of the numerator. Derivative of x is 1. Derivative of y is y prime. It's 1. And then times chain rule times y prime, which makes it y prime, minus the numerator times derivative of the denominator. Derivative of x is 1. Derivative of negative y is also negative 1 times y prime. Any derivative involving y must have a y prime also attached to it because of chain rule. And that's equal to, on the other side, the derivative of y squared, power rule, 2y, right? But then remember, y prime. And derivative of 1 is 0. Okay, so let's see, what are we going to do with this one? For this one, we can actually FOIL things out and combine like terms, right? And in the numerator, I'm foiling the numerator. So I'm going to get x plus xy prime minus y, negative y prime, negative x, and then x times negative y prime, negative times negative makes positive xy prime, negative y, positive y prime, equal, and then we can multiply both sides here by x minus y squared. So the other side is 2y prime times x minus y squared, or cross multiply. Give it a denominator 1 and cross them like that. Okay, so there we have that step, and then we can combine like terms here, right? So the x here, negative x, those are opposites. That's good, those go away. And then we have what, x y prime here, xy prime here. That makes it 2xy prime. And then next we look at y prime, y prime, negative y prime. Those cancel, right? And what are we going to end up with? We're going to end up with negative y and negative y. That's negative 2y. So I combine these two, I did those two, and that's good. The rest of them were opposites on that side and they cancel. Equals to the other side that we have, right? Equals to, oh, because we want to isolate for y prime, so let me just write this as 2y times x minus y squared times y prime. I just rearrange, move y prime in front. Okay, so next step, because I want to divide both sides now by y prime, and this is going to be y prime equals, oh actually, okay, it's too soon to do that. You see that 2x y prime also. Let's move it to the other side. So we get negative 2y equals 2y x minus y squared y prime negative 2x y prime. Now I can factor a y prime and I get 2y x minus y squared negative 2x times y prime. The other side is just 2y because we want to solve for y prime. And then we can do that. So y prime is, divide both sides by 2 divided by Yeah, so it's going to be negative 2y divided by 2y times x minus y squared, negative 2x. And if you factor the 2's out, right, the 2's, all 2's cross out here, okay? And so we're going to end up with, and then I'm going to move, see the negative in the numerator, let me put a step here. And I have x minus y squared minus x, right? So I'm going to actually move the negative to the denominator. So it's going to be y over. When you move negative to the denominator, it distributes to the binomial and negative x, right? Once that's negative, is moved to the bottom. So this becomes actually x minus, and then x minus y squared. We can expand the binomial there. So we're going to get x squared negative 2xy plus y squared. And all said and done, the answer is going to be y over. Then we're going to have x plus 2xy, right, minus hold on, let me check. I see what happened. Okay, I need to bring this y in here also. So there you go. That's the y. Get rid of that. Okay, now when I isolate y prime, so I have y, and then there is a y times the binomial, this right here. Okay, looks better. And then that's going to make this x plus 2xy squared, because I'm distributing the y and removing parentheses, and minus x squared y minus y cubed. And there we have it. So that's, we're going to leave it like that. I'm good with this one. Let's take a look at another exercise. So you see it's a lot of work, huh? It's because the expressions are more complicated and we cannot isolate y. So for instance, we just did 10. Like look at number 14. I wouldn't be able to isolate y even if I wanted to in this one. But the assumption is y is a function of x. It means somehow we could. Now for number 14, let's take a look at 14. So that one is root xy equal x squared plus 2y squared. Let me do number 14. In exercise number 14, if I remember, so that was square root of xy equals x squared plus 2y squared. Okay, same thing. Now remember, square root of xy means xy to 1/2. Okay, so when we do the derivative of the left, we get 1/2 xy to negative 1/2, right? That's just power rule. And then we got to do the derivative of inside, chain rule. Derivative inside is a product, so we go derivative of first by second plus first times derivative of second. That's just derivative of the left side. And the right side, derivative of x squared is 2x, derivative of y squared is 2y, and then y prime. Notice every time I take the derivative of y, there's got to be a y prime next to it because of our assumption that y is a function of x. Now, let's see. So what's going to happen next here is let's multiply. Let me see. I have xy to negative 1/2. Let me see. Okay, so what I want to do is this. I want to factor on the right side, factor a 2. So that's going to equal to 2x plus 2y y prime. Okay, now let's multiply both sides by 2 and xy to 1/2. I'm trying to get rid of that part. Okay, so I'm going to multiply both sides by 2 times xy to 1/2. 2xy to 1/2. Okay. Now on the left side, of course, this is just going to be a 1, so that makes it y plus xy prime, right? And to the right side, we have this more complicated expression. So to the right, we have now 2 by 2. That's going to be 4 xy to 1/2, and then the binomial, right? X plus 2y y prime. All right. And let's take a look and see what we're going to do next. Remember, we're going to have to isolate y prime here, right? So to do that, I'm going to have to distribute this expression to the second term of the binomial because it has y prime, and then move it to the other side at the same time, and bring y to the other side, to the right side. So this becomes xy prime minus 4 times 2, 8, and then we have xy to 1/2, right? It's going to be xy to 1/2, and then times y prime equals, on the other side we have 4xy to 1/2 times x minus y. Okay, so hopefully you can follow this step again. What I did is I brought y, I moved the y to this side. There it is now, right on this side. Okay, and I distributed 4xy to 1/2 times this term, 4 times 2, 8, and then I have y prime and xy to 1/2. I move that over here on the left side. Good. Next, and then of course this part is just when you distribute here. All right, it's looking better. Hard to believe. Now I'm going to factor a y prime, and that's going to be x minus 8 times xy to 1/2 equals the right side. The right side is 4x, right? The right side is 4x times the square root of xy minus y. So y prime is going to be x minus 8 root xy, right? And times y, of course there's a y here too, this y. There is a y in there. And that's going to be times y. And in the numerator we have 4x root xy minus y. And again, notice how complicated these expressions are, is because we cannot solve these explicitly. Let's take a look at one last one from this segment, number 20. In number 20, we have x plus y squared equals cotan xy. X plus y squared cotan xy. Okay, now let's do this one. So exercise number 20. First, I'm going to take the derivative of the left side. Derivative of x is 1, derivative of y squared is 2y, and then y prime. Because of chain rule, remember y is a function of x. That's why y prime shows up. And then derivative of cotangent, that's going to be negative cosecant squared xy, right? That's just derivative of cotangent times. And then we do chain rule for xy. That itself is derivative of first by second plus first times derivative of second. Derivative of y is y prime. Okay, and then we need to isolate y prime. So this becomes 2y y prime. Distribute cosecant squared to the second term of the binomial and move it to the left. The negative becomes positive, and it's going to be x y prime cosecant squared xy, and all that remains on the right side is negative y cosecant squared xy, and of course the 1 moves to the other side, becomes negative 1. And that looks good so far, and we're almost done with this one. Now I can factor y prime times 2y plus x cosecant squared xy equals negative y cosecant squared xy minus 1, and then divide both sides by coefficient on y prime. Let me move these lower. Alright, and then final step, we're going to divide both sides by the coefficient on y prime, which is 2y plus x cosecant squared xy. And on the right side, we can factor negative. So it's going to be negative of that expression. I'm going to go negative 1 plus y cosecant squared xy. And we are done with this one. Okay. Now, let me move these and we'll try these next. Okay, let's take a look at this exercise. This is number 32 we're going to look at. The question actually wants us to find the second derivative this time. So we're going to go ahead and proceed with our first derivative. Now, derivative of tangent of y. So derivative of tangent. One way, by the way, let me show you this. You can think of tangent of y in this section is tangent of a function of x. So you do again work with kind of an outside-inside function. Outside function is tangent, and this would be inside function. Okay, so if you want to find the derivative of tangent, well, derivative of tan is secant squared of whatever inside, and then times chain rule, the derivative of inside, right? Now, we're going to call f of x y, so that's secant squared y times y prime. Okay, so then I'm going to write that. Therefore, number 32, tan y negative xy is 0. Again, this looks pretty innocent to begin with, but it's going to end up being a complicated expression once we get to the second derivative. First one isn't bad. So derivative of tan, I'm going to write it as secant squared y prime. Now, derivative of xy, we have to use the product rule there. Derivative of first by second plus first times derivative of second, and derivative of 0 on the other side is 0. Now, we can factor y prime. This becomes secant squared y minus x. And move y to the other side. And in the next step, we can solve for y prime. So first derivative is going to be y over secant squared y minus x. Again, this isn't bad. This is pretty straightforward at this point. Now, let's take the derivative of this. One thing you couldn't do, by the way, is you cannot take the derivative of the second derivative in that position and at that point. Okay, so we're going to have to solve for y prime and then take the derivative again another time. Okay, I mean you could, but it's going to be really messy if we proceed this way. Okay, but we could, but I rather isolate y prime and then take the second derivative that way. So let's take the second derivative now. Y double prime is going to be, so we're going to use the quotient rule, right? And we're going to square the denominator. That's secant squared y minus x quantity squared. Repeat the denominator, minus x quantity squared times the numerator, which is just, or actually times derivative of numerator, which is going to be y prime, right? Oh, actually, I'm sorry. This is a squared. We repeat the denominator before we square it. Okay. Times derivative of numerator is y prime minus y times, now derivative of the denominator And remember, we're taking derivative of this denominator, not this denominator. So derivative of secant squared y. Now secant squared y, that's secant of y quantity squared. So we do have an outside function, which is the power function, not the power function, but the power function to a power. Because power functions are in this form. That's not what that is. So it's a function to a power. The derivative of this itself is just 2 secant y, right? And then the derivative of inside, that's going to be another secant tan. And then remember, y itself is a function of x, so there's a y prime here. So when we put it all together, and I'm going to have 2 secant squared y tan y, and then minus 1. That's the derivative of x, right? Remember, I just took the derivative of denominator, so that's this derivative. Okay. Now, next step, let's clean this up a little bit. One thing I need to do now, I need to plug in y prime in there. And you can see it's going to get messy, right? Because it's a fraction that we're going to have to plug in. So this is going to equal to secant squared y minus x times y prime, which we just did, y over secant squared y minus x, right? And let's make this all over. And we're going to square the denominator, right? So squaring the denominator, we get secant, or actually it's already squared. We did that. I'm just copying the denominator. So I replace y prime in the numerator minus everything else, right? Minus y2. Or let me just I'm debating. Yeah, let me distribute the y. So I'm going to get negative 2y secant squared y tangent y. And then negative y times negative 1, that's just going to be plus y. Okay. Now, we do have a fraction in the numerator, right? We do have a fraction in the numerator. We could get rid of that fraction by, let me see, they're the same thing, so I can actually cancel these, right? We could cancel them. But one thing I need to do is, let me hold on. Okay, I see what I didn't do here. See this y prime? That's times y prime, and then plus y. Okay, so that means I actually have to substitute for y prime in here as well, right? So I'll do that in the next step. Okay, and also I'm going to cross these binomials out. So I'm going to get y minus 2y secant squared y times tangent of y times y over secant squared minus x y over secant squared y minus x. Okay, and then so that's what y prime is right in here. Okay, and then plus y, all of that divided by secant squared y minus x. I knew that's going to be messy because of what you're seeing unfolding. Now we do have a complex fraction that is a fraction over the main fraction, which I just got rid of, over the main fraction. So what I need to do to get rid of that is I'm going to multiply the entire top by secant secant squared y minus x. Okay, That's what we're going to multiply them by. Okay, so that's what I'm going to do. Multiply by secant squared y minus x. Okay, and the bottom as well. It's going to be secant squared y minus x. Now let's distribute. And also note we have a y here and a y here. So those are like terms. So we got two y's. Those combine. And so I'm going to combine them and multiply it by this factor that I just multiplied the top and the bottom by. So it's going to be 2y, and I'm going to distribute the factor to those. And also this factor distributes to this expression. Now this is a long expression. See, all of this is all part of one expression. When we distribute, we're going to lose secant squared y minus x from the denominator of this fraction. Okay? And that long expression is going to become negative 2y squared. And then I have secant squared y tan y, right? And that's it, because the denominator divides out. Now, how do I get y squared? Because y multiplies by this y. Those give me 2y squared. And then secant squared y tan is there. All right, we're good with this one. All of that divided by now secant squared y minus x cubed. Okay. And all I can do is now factor 2y from the numerator. That's going to be 2y, and then I have secant squared y minus x negative y, because I have y squared, 2y squared, 2y's factored out. Then I have secant squared y, and then tan y. And all of that divided by the denominator. And that's as simple as this can get, which isn't really that simple. And this would be the second derivative. Okay, so we're done with this one. This one, and not for the faint of heart. It's kind of messy, but that's how this is, unfortunately. I don't know what to tell you. Let's take a look at another exercise here. Let me bring up this next exercise. Okay, now in exercise number 38, the question reads, find the equation of the tangent line to the given curve at indicated point. The point that they have in mind is negative 2 root 3 comma 1. Now square root of 3 is going to be approximately 1.7 times 2, that's negative 3.4-ish, 3.5-ish, so, and 1, that would be about here, right, that point. And we want to find the slope of a tangent line. That's the tangent line at that point. So this one is called conchoid. It's a conchoid of Nicomedes. All right. And you can see, by the way, this is not even a function, right? It fails the vertical line test at every point. But yet we can find the derivative. So that's the advantage of implicit differentiation. We don't even need to have a function. We can do this for any equation, provided the assumption that we make still holds. Okay, so let's take a look at this one. First, we gotta find the derivative, and then we plug in xy. Now, because we're given a point here, we don't have to really go all the way and do all the dirty work to try to get it down to where we isolate for y for this one. We could, but it's a lot of busy work that's not necessary. So let's take the derivative, and then we just directly plug it into it. Okay, and that's helps us find y prime, which is the slope of a tangent. Now they want the equation of the tangent, so first we need to find the slope. So here we go. On the left side, it's the product rule. So the derivative is going to be what? It's going to be 2x, derivative of first by second, plus x squared, and then derivative of y squared is 2y, remember, y prime. And that's going to equal to, on the other side, we have the product rule, right? We got the product rule on the other side also. Derivative of y plus 1 squared, that's going to be 2 times y plus 1. And the derivative of inside is just 1, so we don't write that. Times 4 minus y squared. The derivative of inside is 1, and then we go y prime, right? Every time we take derivative of y, there's a y prime. Times 4 minus y squared. Plus, so we did the first, we did derivative of first by second, now we do f g prime. Plus y plus 1 squared times derivative of 4 minus y squared is negative 2y, y prime. Correct? And then we can simplify this somewhat. And again, I said I don't want to do it completely, but let's just tidy up a little bit. So this is 2x y squared, right? And then plus 2x squared y prime. I'm just organizing some things here. And then put y prime, 2y plus 2, distribute the 2, and then 4 minus y squared, plus, just the latter part is negative 2y, y prime. Oh, let me write that as like this, y prime times negative 2y by y plus 1 squared. Okay, so if you did want to actually isolate for y prime now, you could a lot easier. All right, but let's actually plug in at the given point. Okay, at given point, so that means at negative 2 root 3 comma 1. That's x and this is y. Let's plug those into it. So we're gonna get, okay, so let me plug it in. I'm plugging into that equation. Okay, 2x, that would be 2 times negative 2 root 3. Okay, and then let me shrink it a little bit. Okay, and then times y squared. Y is 1, so that's going to be 1 squared plus 2 times x squared, that's negative 2 root 3 quantity squared, root 3, that quantity squared, times 1 times y prime equals y prime. The right side is entirely made up of y and y prime. That's good because y is 1. That's 2 times 1 plus 2, 4 minus 1 squared, and then plus y prime, negative 2 times 1, and then 1 plus 1 quantity squared. Okay, so this is going to be 3 times 4, and that's 12. We have 12 y prime, and then 2 squared is 4 times 2, negative 2 that is, makes negative 8 y prime. So we resolve the right side. The right side is just going to be 4y prime. Now on the left side we have, right in here, that's going to be root 3 squared is 3, 2 squared is 4. Negative squared becomes positive, and then 2 in front. So that's going to be 24y prime. And then in front, right in here, we got negative 2 times 2, that's negative 4 rad 3. Okay, I'm going to subtract 24y prime from both sides, and that makes it negative 20y prime on the other side. So y prime must be 4 root 3 divided by 20, divide the 4's out, that's root 3 divided by 5. So that's going to be the slope of the tangent line. The equation of tangent is what they want, and that's going to be y minus y1 mx minus x1, and that's y minus y1 is 1, slope is root 3 over 5, and x minus x1 was negative 2 rad 3. There you go. So that's going to be the equation, and of course we can isolate for y. So y is going to be root 3 over 5, that's the slope, and double negative makes positive here, positive 2 root 3, so I have 2 rad 3 times root 3 over 5 in front. That's 2 by, this is 3, root 3 is 3, 3 by 2, 6, that's 6/5. So it's going to be positive actually, because negative by negative is positive, plus 6/5 and plus 1. And that's going to make it 11/5, right? So the final answer to this is the equation of a tangent is 11/5 plus root 3 over 5x. And there we have this one. Okay, and we did find the equation of tangent in this one. Let's take a look at one last problem. This is actually an application problem that we're going to take a look at. So let me shrink this a bit, and let me fix this image for a moment. Okay, let's take a look at this exercise. In exercise number 46, this is the last one for this section. The question reads, watching a rocket launch, and the problem goes, at a distance of 2,000 feet from the launch site, a spectator is observing a rocket 120 feet long being launched vertically. Let theta be her viewing angle of the rocket, and let y denote the altitude measured in feet of the rocket. Neglect the height of the spectator. Okay, now in part A, we want to show that tangent of theta, remember theta is the viewing angle of the spectator. Okay, we want to show the tangent of theta is 240,000 divided by that expression. Okay, now in order to use our trig ratios like tangent, sine, cosine, remember those are measures of right triangles. This triangle that you see here, that's not a right triangle. Okay, this is not a right angle. So that means we got to do something different. So for this one, we can say that if this is angle alpha and this is the measure of angle beta, therefore angle theta here is simply alpha minus beta, right? And then we actually have an identity for tangent of alpha minus beta now, which would be tan theta. So let me write tan theta, that's what we want to show. That's going to be tangent of alpha minus beta. Now, alpha, we are given all of this information. So for the larger triangle, that's this triangle, tangent of alpha we can find, and for the smaller triangle also we can do that, right? There you go. Both of these now end up being right triangles, and we can find those tangents. But first we need to write down the tangent of difference identity, and that's going to be 1 plus tan alpha tan beta, and in the numerator we have tan alpha minus tan beta. So you should recognize this identity. That's from your trigonometry. So let's actually work tangent of alpha here. So what is tangent of alpha? we're looking at the bigger triangle here, right? Tangent is opposite over the adjacent, right? The side opposite, which is y plus 120 divided by the adjacent side, which is 2,000 feet. And then tangent of beta, likewise, for the other triangle, the smaller triangle, that's just going to be y over 2,000. All right? So we can plug these in now into our tan theta formula. So that tangent of theta is going to be, in the numerator, we have tangent of alpha minus beta. So that's going to be y plus 120. Hold up. Okay, so it's going to be y plus 120 divided by 2,000. That's tan alpha minus the next fraction is y over 2,000, right? Divided by 1 plus their product. That's y plus 120 over 2,000 times y over 2,000. And we can work this one again. It is a complex fraction, so we're going to multiply top and the bottom by the LCD. The LCD here, of course, being 2,000. So I'm going to multiply the top by 2,000 and the bottom by 2,000. Okay. And when we do, we're going to distribute 2,000 to the first fraction. So that's tan theta equal. We're going to lose the denominator, right? When we distribute 2,000, so it's just y plus 120 minus y. In the denominator, 2,000 times 1 is 2,000. And actually, the LCD is 4 million. Sorry. Because see, you got two 2,000s down here. We got to get rid of both of them, don't we? So I'm going to write 4 million here. There, and 4 million there. Now, that's going to change this ever slightly. 4 million times the fraction divided by 2,000, that's 2,000 times y plus 120 minus 2,000 y, right? 4 million divided by 2,000. And in the denominator, we're going to have 4 million times 1 is 4 million, plus 4 million times the fractions. The 2,000 crosses out, so I'm going to get y squared plus 120y in the denominator, distributing the y to the binomial. And in the numerator, negative 2,000y and 2,000y cross out, and we have 2,000 times 120. That's going to be 240,000. And in the denominator, put them in descending powers of y. And we get the desired results. That's what we want to show, that tangent of theta is that expression right up here. Okay, and then in part B now, let's see, in part B, the question goes, what is the viewing angle when the rocket is on the launching pad? Okay, well, when the rocket is on the launching pad, you know, the spectator is right in front of the spectator, right? So at that point, the height of that launch is 0, right? Y is 0. So the viewing angle is going to be very small, right? Therefore, when y is 0, tangent of theta is, you just plug in 0 here and here in the denominator, and we're going to get 240,000 divided by 4 million. Okay, and then you take inverse tangent of that, right? The arctan of that, but the number 240,000 by 4 million is going to be 0.06. Okay, that's tan theta, 0.06. So the measure of the angle, therefore theta is going to be arctan of 0.06 radians, that is. Make sure your calculator is in radian. And we go 3.43 degrees. Okay. And of course, the other angle would be 183.43, but we want the answer that's in the first quadrant, right? Because there you go. Right in here. This is the rocket, and this is the viewing angle theta. We can assume that the spectator is at the origin of the coordinate system. So the angle is going to be very, very tiny angle, 3.43 degrees. And then continuation of part B, the latter part of part B reads, when is it at an altitude of 10,000 feet? That is, what is the viewing angle when it being the rocket? When the rocket is at an altitude of 10,000 feet. So when y is 10,000, you just plug in 10,000 now, just like we did earlier for y. So the numerator again remains 240,000 divided by denominator. Put 10,000 for y, you square it, plus 120 times 10,000 plus 4 million. These large numbers we're working with. Okay. Now, let's see this. The computation for all of this, let me do it on my calculator. Okay, so I did the computation and I got 0.00228. Okay, and then if I take again the arctangent of that, arctan of 0.00228, a very small number, that answer is going to be about 0.13, and that's going to be in degrees. Okay. Also, let me mention how I got these numbers again. I forgot to point this out. When you actually work, I'm up here. When you actually work that number, the arctan of 0.06. So for that answer, arctan of 0.06, that one I got this to be 0.0, let's see, 599, and then multiplied by 180 divided by pi, and that's how I got 3.43 times 180 degrees by pi. Because remember, these are in radians. Okay, so that's how I got this number times 180 divided by pi gives you that number. Same thing with this one. Let me actually put down what I got here first before the 0.13. So if you do on your calculator, make sure you are in radian mode again, okay? So this number turns out to be 0.0228 in radian. Hold on. Okay, just a moment. Okay, so this actually turns out to be almost the answer itself, 0.0228, and then I'm going to multiply by pi by 180 divided by pi to convert it into degrees. Okay, and that's how I got that number. So it's 0.00228 times 180 divided by pi, and that's 0.13 degrees. Okay, so the viewing angle at the launch pad is small, but notice once the rocket reaches 10,000 feet altitude, that viewing angle is almost diminishing, isn't it? It's getting very small. So in part C now, it says find the rate of change of the viewing angle when the rocket is at an altitude of 10,000 feet. The rate of change of viewing angle. So that means we gotta find the derivative, right? In part B, the derivative of tangent theta. derivative of this tan. So remember, tan theta we said is equal to 240,000 divided by at the moment it's at 10,000 feet. Okay, that's over y squared plus 120y plus 4 million. Now we're going to do this with respect to theta, right? That's what we're told. And because we want to, again, the question reads the rate of change of the viewing angle. That's theta. So we want to know how much theta is changing. So that means we're going to change the derivative of part B. Then we're going to have to do implicit differentiation with respect to y here. Okay, so the derivative of tangent theta is going to be what? Secant squared theta, right? And then the theta dy, okay, or theta prime, if you want. The theta dy is theta prime, because we assume theta is a function of y, right? The viewing angle is a function of altitude of the rocket. And the right side for this one, we can, let's see, do the quotient rule. 240,000 is constant. So here's what the right side's gonna turn out to be. Let's do that derivative here. Now 240,000 is constant multiple, right? So I'm going to write 240,000. So I want to find the derivative of 1 over y squared plus 120y plus 4 million. Okay, that derivative. So we can use the quotient rule, right? The derivative of that is, you repeat the denominator and you square it. We have to square that. Now repeat the denominator, y squared plus 120y plus 4 million times derivative of 1 in the numerator, which is 0, minus, that makes this, all of this 0, times 0 is 0, minus the numerator times derivative of the denominator, which is 2y minus, or 2y plus 120. Right? Derivative of y squared is 2y, and then plus 120. So that's going to be, and notice it's going to be negative, right? So I'm just going to have negative 2y plus 120 in the numerator, and in the denominator we have the function, the polynomial function, y squared plus 120y plus 4 million. All right, so there we have that one. Now, at this point, we're going to just find the derivative. The theta dy is going to be equal to, I'm going to divide both sides by secant squared theta. Okay, so it's going to be y squared plus 120y plus 4 million times secant squared theta, and in the numerator, of course, we have the negative 240,000 times 2y plus 120. Okay, now at this point, because we're given tangent of theta, right? Tangent of theta. So we need to actually change our secant using tangent identity, right? Because we have tangent of theta, right? We found it to be right here in part B. Because the altitude 10,000, they kept it the same. So we can actually use this expression. Tan theta is this one. Is 0.00228. That means I can use the Pythagorean identity for the denominator. So this is going to be let me just write here secant squared. This is 1 plus tan squared theta. So you can use tan squared from part B. Okay. So d theta dy is therefore going to be negative. Well, let me move down because it's going to take up a long line here. So it's negative 240, 1, 2, 3 zeros. Okay, 2y, y is 10,000 times 2, that makes it 20,000 plus 120 divided by 10,000 squared plus 120 times 10,000 plus 4 million, and that multiplies by 1 plus, remember tan of theta was 0.00228, right? And that's squared, that's tan squared. Okay, and then you reach for the calculator at this point. That's what I'm gonna do. Okay, let me make sure before I punch in my calculator these numbers, and let me make sure I got everything done right. So I took the derivative, I'm up here. I took the derivative and then the derivative of the right side. You know what I didn't do? I did not square the bottom, the denominator of the right side when I used I did it here, right? Down here, I did it, but I didn't transfer the 2 here. So this should be squared. Now it looks better. And that's squared. Please make a note of that. Be careful with that. Don't make the mistake I made there. That's squared over this thing. So that's going to be squared times 1 plus tangent, which is 0.000, right? How many zeros we had? Quite a few zeros. 2 zeros, 228. Okay, 228, and then that's that squared. Why? What a messy problem, right? Okay, but that looks good. So now I'm gonna calculate this. When all of this is done, and you're gonna get really huge numbers in the denominator. Okay, and all said and done, what I got as a result is negative 4.34 times 10 to negative 7 for this. Okay, and this is going to be radians per feet. The negative means the viewing angle is changing, means it's shrinking, right? The rate of change is decreasing, right? D theta dy is approaching 0. It's getting smaller, smaller, smaller. And this is radian per feet. And then if you do times, if you multiply by pi over 100 or 180 divided by pi, that will convert it to degrees, and I got for that, I got 0.00025, and this is going to be degrees per foot. So that's, and it's going to be negative, of course, right? Because we start with negative angle. Then the rate of change is negative. So it's decreasing, so it looks like the viewing angle is diminishing, right? And that should answer part D. In part D, what happens to the viewing angle when the rocket is at a very great altitude? Means as y approaches infinity, right? For the answer to that, we're going to say the viewing angle approaches 0. Angle approaches 0. Okay, as the altitude increases. So, and there you go. That's why when things move up, they get really small, right? But anyhow, we are done with this lecture. So we're done with section 2.7. Again, we looked at implicit differentiation here. And with that, I'm just gonna make sure everything is looks right. And boy, we did a lot, huh? Okay, we're good. So this completes section 2.7, implicit differentiation.